One of the outputs from your GPS receiver is the displayed latitude and longitude coordinates of the ship's position. That latitude and longitude of the GPS output can be plotted on a nautical chart. The navigator is then able to see his boat's position in relation to the navigational hazards nearby. He is also able to see his boat's position in relation to the intended course line and his last plotted position. He can then adjust his course, as required. We put lines on the nautical chart where the line of latitude from the GPS and line of longitude from the GPS intersect. The lines of latitude and longitude are position lines, and where they intersect is a position fix. The position fix on the nautical chart from the latitude and longitude display of GPS follows the same principle of position lines. Your GPS receiver uses direction and distance information from multiple satellites, and calculates the antenna's position and displays it in latitude and longitude. The satellites can be considered to be artificial celestial bodies, and the computer in the receiver can do more calculations, faster than we ever can. We get the convenience simply looking at a screen and plotting two short lines to know where we are, in any condition of visibility or time of day. The Global Positioning System, GPS, is a network of about 30 satellites orbiting the Earth at an altitude of 20,000 kilometers. The system can be used by anyone with a GPS device can receive the radio signals that the satellites broadcast. That device can be a sat-nav, mobile phone, watch or handheld GPS unit. A GPS satellite is a satellite used by the Navstar Global Positioning System. The GPS satellites complete 2 full orbits of Earth every day. GPS satellites travel at approximately 14,000 kilometers per hour, relative to the Earth as a whole, as opposed to relative to a fixed point on its surface. Geostationary orbit means having a circular orbit that lies in the plane of the Earth's equator. And a polar orbital plane means having an orbit that passes over the Earth's poles. GPS satellites do not orbit in a geostationary or polar manner. The satellites in the GPS constellation are arranged into 6 equally spaced orbital planes surrounding the Earth. Each plane contains 4 slots occupied by baseline satellites. Wherever you are on the planet, at least 4 GPS satellites are above your horizon at any time. Each one transmits information about its position in the current time at regular intervals. These signals, traveling at the speed of light, are intercepted by your GPS receiver, which calculates how far away each satellite is based on how long it took for the messages to arrive. Once it has information on how far away at least 3 satellites are, your GPS receiver can pinpoint your location using a process called Triliteration. When a GPS receiver is switched on and there are 3 satellites above your horizon, the GPS receives a signal from satellite A that includes the distance between the satellite and the receiver. But because of the shape of the Earth, there is a circle of places at distance from the satellite. We know the receiver must be located somewhere on the first circle. If the GPS receives signals from a second and third satellites, B and C, the receiver calculates and displays where the 3 circles intersect. Please note that GPS receiver actually generates a sphere of information. Surface craft like ships use the circle on the Earth's surface, but aircraft and mountaineers will use the overlapping spheres rather than circles. The more satellites there are above the horizon, the more accurately your GPS unit can determine where you are. There is a note on nautical charts of Trinidad that says, positions are referred to WGS84 datum. The World Geodetic System, WGS, is a standard for use in cartography and satellite navigation including GPS. The World Geodetic System in use since the early 1980s is called WGS84. The WGS84 system includes defining parameters including the location of the Earth's center of mass, the Earth's equatorial radius and the flattening at the poles, the WGS84 meridian of 0 longitude and the angular velocity of the Earth. The WGS84 0 meridian is 102 meters east of the Greenwich meridian at the latitude of the Royal Observatory. Many people are familiar with car-installed GPS units, and motorists who are also navigators, are applying that same level of trust to the GPS unit system on board the vessel. On the road, inaccuracies can easily be recognized by the driver through referencing visual landmarks, like buildings or the street. This ready reference is often not available to the vessel operator on the water, and keeping a proper lookout is still vitally important. Prudent navigators use all available cues to maintain situational awareness and never rely exclusively on a single source of navigation data. It is best to remember a GPS unit is a navigation aid, not a substitute for the human eye and common sense. The software installed on a GPS unit includes geographic reference and can include aids to navigation marks and, in more advanced models, link to depth sounders to provide indications of water depth. GPS was upgraded in 1995, following some commercial aviation disasters which were caused by inaccurate navigation information. Recent incidents involving vessel collisions with maritime or navigation infrastructure have been caused by an over-reliance on GPS technology, or the use of an inconsistent datum applied to the GPS unit, or the electronic chart not being updated. GPS satellites broadcast their signals in space with a certain accuracy, but what the receiver gets depends on additional factors, including satellite geometry, signal blockage, atmospheric conditions, and receiver design quality and features. Some of the limiting factors of using GPS include ionospheric and tropospheric interference, satellite positioning, calculating ability and accuracy of the GPS unit, natural or artificial interference, horizontal chart datum and chart reliability. Under the best conditions, the horizontal accuracy of the GPS system is approximately 3 to 8 meters 95% of the time. Vertical accuracy is considerably lower. Nautical Charts of Trinidad has a note about the sources of the information on the chart. The note reads, in part, the origin, scale, date and limits of the hydrographic information used to compile this chart are shown in the source diagram. Depths in upright figures are from smaller scale charts. This slide shows the source diagram on chart 483. The source diagram tells us, for example, that the charted depths on Couva Shoal are from surveys done in the 1920s and 1930s. Chart 500, northeast approaches to Trinidad. The chart title states that positions are referred to WGS84 datum. This chart also has a note, chart accuracy. Owing to the age and quality of the source material, some detail on this chart may not be positioned accurately. Particular caution is advised when navigating in the vicinity of dangers, even when using an electronic positioning system such as GPS. Chart 1044. Trinidad and Tobago to Archipelago Los Testigos, including Grenada. The chart title states that positions are referred to WGS84 datum. This chart also has a note, chart 517, positions. Positions on chart 1044 differ from those on chart 517 by varying amounts. Positions should be transferred by bearing and distance from common charted objects, not by latitude and longitude. Chart 481, Serpent's Mouth. The chart title states that positions are referred to WGS84 datum, except in Venezuelan waters where the datum is not known. This chart also has a note, caution, satellite-derived positions. Positions obtained from satellite navigation systems, such as GPS, are normally referred to WGS84 datum. In Venezuelan coastal waters, the difference between satellite-derived positions and positions on this chart cannot be determined. Mariners are warned that these differences may be significant to navigation and are therefore advised to use alternative sources of positional information, particularly when closing the shore or navigating in the vicinity of dangers. Elsewhere on this chart, positions can be plotted directly. A hydrographic survey is the measurement and description of features which affect maritime navigation, marine construction, dredging, offshore oil exploration, offshore oil drilling and related activities. There are several reasons why hydrographic surveys are important, with the main purpose being for navigation. When ships or fishing boats are out on the water, they use hydrographs to establish whether an area is safe to head into, either in advance or while on the water. The results from a hydrographic survey are normally plotted to produce a bathymetric contour map, which is a plan of the depth of the seabed arranged in such a manner as to show lines of equal depth from the coastline. In a hydrographic survey, the actual measurement of the water depth is the easy part. The usual method of sonic depth measurement consists of running a succession of parallel sounding lines across the survey area. The resulting sounding procedure cannot provide complete coverage of the sea bottom. The coverage of the sea bottom obtained depends on the water depth, the line spacing and the echo sounder's beam width.